October 12th, 2025. It's been 8 days since the last official update dropped about 3 Atlas, that cosmic wanderer from beyond our solar neighborhood that's been cruising past our sun while dropping hints of chemistry that doesn't belong here. No crystal clear photos, no straight answers, just a carefully packaged story stamped comet and served up for public consumption. But is that the real story? The cracks in this narrative are getting wider by the day. And tonight, we're peeling back the layers to ask the question that's on everyone's mind, but nobody's daring to say out loud. Are we getting the truth? Or is there something major happening behind the curtain? And sticking with our new multi-story format, the revelations only get darker from here. We'll dive into the rogue black hole, silently drifting through our Milky Way, an invisible predator that could rewrite everything we thought we knew about cosmic safety. We'll confront the massive wound tearing open on our sun right now, one that could disrupt far more than our skies. Then we'll tackle the ultimate countdown. Scientists warning that the universe itself might collapse in a big crunch with a timeline that's way shorter than you'd think. And if that wasn't enough to keep you up at night, satellites are falling back to Earth every single day, 1 to 2 daily to be exact. The real question is, why isn't anyone talking about this? If these mysteries have you hooked the way they've got me, make sure to hit that like button and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and whether you believe we're getting the full truth about these world-changing discoveries. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1. The arrival nobody can agree on. On July 1st, 2025, something arrived not from our sun, but from the depths of interstellar space and immediately set off alarm bells in all the right places. You probably didn't hear about it. Most people didn't. But in the quiet corners of astronomy departments and research stations scattered across continents, scientists started exchanging encrypted messages, scheduling emergency conference calls, and staring at data that refused to behave the way data should. They called it 3 Atlas, catalog designation C2025. A1, the Atlas Survey telescope in Chile, spotted at first faint smudge moving against the background stars with a trajectory that told an impossible story. This was only the third confirmed interstellar object humanity had ever detected, following the famous Oumuamua in 2017 and comet Borisov in 2019. Remember Oumuamua? That cigar-shaped mystery that accelerated in ways gravity alone couldn't explain, that refused to outgas like a proper comet, that vanished back into the cosmic ocean before we could get a good look at it. Atlas was different. Or maybe it was the same. Nobody could quite agree. The orbital mathematics told one story clearly enough. This object was moving on a hyperbolic trajectory, meaning it wasn't bound to our solar system. It came from somewhere else, somewhere unimaginably distant, and it would leave again, disappearing back into the gulf between stars. The inbound speed clocked at roughly 60 kilometers per second, which translates to about 130,000 miles per hour. If you prefer your cosmic velocities in more terrestrial units, that's faster than anything human-made has ever traveled. faster than the solar wind, fast enough that when you do the math backwards, when you trace that trajectory into the past, you find yourself pointing toward a region of space where no known star should ascend it. The object would reach perihelion, its closest approach to the Sun, on October 30th, 2025, passing within approximately 1.4 astronomical units of our star. For reference, 1 astronomical unit is the distance from Earth to the Sun. So Atlas would swing inside the orbit of Mars, but remain comfortably beyond Earth's own path. The closest Earth approach would be about 1.8 astronomical units, far enough that even the most paranoid among us couldn't credibly claim it posed any collision risk. This wasn't melancholia. This wasn't don't look up. The danger, if there was any danger at all, wasn't kinetic dot. But then the anomalies started piling up like evidence bags at a crime scene investigation. First came the size estimates. Initial calculations suggested Atlas might be tens of kilometers across, substantially larger than either of its interstellar predecessors. Other estimates disagreed wildly, suggesting something much smaller but with unusual reflective properties. The uncertainty itself was strange. Modern astronomy has gotten very good at sizing up rocks in space. When estimates vary by factors of 10 or more, something about the object's surface or shape is confusing our instruments in ways that shouldn't be possible for a simple comet. Then the chemistry reports arrived, and they made no sense at all. Most comets, when they warm up approaching the Sun, begin to outgaze as volatile ethers in their nuclei sublimate, away in beautiful tails that stretch millions of kilometers across the solar system. Atlas didn't follow this script. Spectroscopic analysis showed carbon dioxide dominating the outgassing with water barely present. Even stranger, some observations detected high concentrations of nickel in the emissions, an element that has no business appearing in such quantities in a natural comet's exhalation. You might think astronomers would be shouting about this from the rooftops. You might imagine emergency press conferences, rushed papers, telescopes around the world pivoting to track this bizarre visitor. Some of that happened certainly, but much of the response was muted, cautious, hedged with qualifications and maybes. Many astronomers publicly treated Atlas as simply a strange but natural comet, an outlier in the distribution, but not fundamentally inexplicable. Comets are diverse, they reminded us. Each stellar system has its own chemistry. We shouldn't expect every visitor to match the composition of objects born in our own cosmic neighborhood. And yet, there were whispers in the comment sections of preprint papers, in the quiet conversations at conferences, in the encrypted chat channels where researchers speak more freely than they do in peer-reviewed journals. Some were asking the question that dances at the edge of respectability in modern astronomy. What if Atlas wasn't entirely natural? What if we were looking at something engineered, something technological, something sent? The word probe began appearing, usually buried in conditional clauses and The word alien was spoken even more quietly, often with a nervous laugh, attached a social signal that the speaker knew they were treading on dangerous ground. Careers have been damaged by taking such suggestions too seriously. Reputations have been built on dismissing them. But the numbers didn't care about reputations. The chemistry didn't care about careers. And as October approached, as Atlas drew nearer and our telescopes gathered more light from its surface, the anomalies didn't resolve themselves into comfortable explanations. If anything, they multiplied. So here we are, an object from another star system is passing through our cosmic backyard right now. As you listen to these words, it's displaying characteristics that don't quite fit any model we have for natural bodies. The data we're seeing is incomplete, scattered, sometimes contradictory, and the institutions we trust to make sense of such things are speaking in careful, measured tones that might be scientific caution or might be something else entirely. The question isn't whether Atlas is strange. Everyone agrees it's strange. The question is what kind of strange we're dealing with and who gets to decide. In the next part, we'll dig into the pulses, the spins, and the question that keeps a certain type of scientist awake at night. Is it signaling or just tumbling through the void? Pulses in the dark signal or spin. Light tells stories if you know how to read it. Every photon that reaches our telescopes carries information encoded in its wavelength, its polarization, its timing. When astronomers study an object like Atlas, they're not just looking at a dot in the sky. They're analyzing how that dot's brightness changes over time, constructing what's called a light curve graph that maps illumination against hours and days and weeks. Most comets produce messy, chaotic light curves. They tumble irregularly through space, their rotation destabilized by the uneven forces of Algazine. Their surfaces, pockmarked and asymmetric, the brightness variations we see are essentially noise. Random fluctuations as different surface features catch the sun's light at different angles. It's the optical equivalent of white noise, predictable only in its unpredictability. Atlas didn't follow this pattern, or rather, it did and it didn't, which might be even more unsettling. The light curve showed variations that were unusually regular brightness changes that repeated on precise timescales, suggesting a structured geometry rather than chaotic tumbling. Some sections of the data displayed periodicities that made astronomers lean closer to their monitors, double-checking their calibrations, wondering if they were seeing what they thought they were seeing. The technical term is photometric periodicity, and it's exactly what you'd expect from a spacecraft deliberately rotating to control its orientation, or from a probe designed to flash patterns into the cosmos, or from any number of engineered systems that require precise control of angular momentum. It's also, to be fair, what you might see from a natural object with an unusual but still explicable shape, perhaps a contact binary, two lobes connected by a narrow neck spinning in a stable configuration. But then the polarization data arrived, and things got weirder. Polarization measures how light waves are oriented as they travel through space. Unpolarized light vibrates in all directions perpendicular to its path of travel. Polarized light vibrates in specific planes, and the degree and direction of polarization tell us about the surface properties of whatever reflected or scattered that light. Rough surfaces depolarized light. Smooth surfaces can create strong polarization signatures. Certain geometric arrangements produced what's called negative polarization, where the polarization flips in a direction opposite to what you'd normally expect. Atlas displayed extreme negative polarization at certain angles, values that push the boundaries of what models predicted for any known natural surface composition. One paper described it as anomalous polarization behavior inconsistent with standard cometary dust models. Another used the phrase geometric albedo, features suggesting non-random surface structure. These are the kind of careful, heavily qualified statements scientists make when they're seeing something that doesn't fit. But they're not quite ready to say what they think it might actually be. Imagine a lighthouse. The beam sweeps across the ocean at regular intervals, a precisely timed pulse that carries information to any observer with eyes to see. Now imagine that lighthouse is tumbling through space at 60 kilometers per second. And instead of a beam of light, it's reflecting sunlight in patterns that repeat too regularly to be random, but not regularly enough to be definitively artificial. That's approximately what we're dealing with here. It might be a beacon, it might be the universe's most inconveniently shaped rock. The non-gravitational acceleration data added another layer to the puzzle. When you track an object's orbit with sufficient precision, you can detect tiny deviations from the path pure gravity would prescribe. Comets show these deviations all the time, outgassing acts like a weak rocket engine pushing the comet slightly off course in directions determined by where the gas is venting from the surface. For a normal comet, these forces are symmetric on average, smoothing out over time. For Atlas, the non-gravitational acceleration showed patterns that were difficult to explain with standard outgassing models. Some researchers proposed the object was what's called a dust-rich comet, a dirty rock shedding primarily solid particles rather than gas, creating forces through the radiation pressure on those particles rather than through volatile venting. This would explain some of the chemical oddities and some of the acceleration anomalies. It was a good hypothesis, a reasonable compromise between just a weird comet and possible alien probe. It didn't explain everything, but it explained enough to be respectable. And maybe that's what it was. Maybe Atlas was simply occupying a poorly explored region of the parameter space of possible cometary bodies, showing us that our models needed refinement rather than replacement. The universe is under no obligation to make sense to us. It doesn't care if we find something confusing. It just is. Indifferent to our desire for clean categories and comfortable explanations. But here's what kept nagging at the researchers who studied those light curves late into the night. If you wanted to send a probe to another star system, if you wanted that probe to be detectable but not obviously technological, if you wanted to walk the line between look at me and I'm just a rock, what would you design? You'd probably create something that looked mostly natural, that could plausibly be dismissed as a comet or asteroid, but that showed just enough geometric regularity to catch the attention of anyone looking carefully. You'd want ambiguity. You'd want deniability. You'd want observers to argue among themselves about what they were seeing. And that's exactly what we got. The radio astronomers found nothing. Of course, no clear periodic signals, no modulated carrier waves, no beacon transmitting across the electromagnetic spectrum in ways that would scream artificial. But absence of evidence isn't evidence of absence, particularly when we're only listening across a narrow range of frequencies, when our radio telescopes can only point at limited windows, when the object is moving so fast that any signal would be heavily Doppler shifted and potentially unrecognizable. So we're left with ambiguity, patterns that might be signals or might be spin, chemistry that might be alien or might just be from a very different stellar nursery than our own. Acceleration that could be outgassing or could be something else. Every data point has two interpretations, sometimes three, and choosing between them requires either more information than we have or a leap of faith in one direction or another. How does this compare to the other interstellar visitors we've detected? What does the historical record tell us about objects that don't quite behave? That's where we turn next to the shadow of Oumuamua and what it taught us about seeing clearly. The Oumuamua shadow, October 19th, 2017. The Pan-STARRS telescope in Hawaii flagged an object moving through the inner solar system on an impossible trajectory. At first, astronomers assumed it was an asteroid or comet from our own Kuiper belt, perturbed inward by some gravitational interaction. But within days, as more observations accumulated, the orbital calculations converged on a disturbing conclusion. This object, soon named Oumuamua for scout or messenger, had come from interstellar space. It was the first time in human history we'd confirmed an object passing through our solar system that originated elsewhere. The first time we could definitively say we were witnessing a visitor from another star. And it was bizarre. Oumuamua accelerated as it departed the solar system, small but measurable push that couldn't be explained by gravity alone. It showed no cometary tail, no outgassing, no visible signs of the volatile gases that should sublimate when warmed by the sun. Its shape, inferred from the way its brightness changed as it tumbled, suggested something extremely elongated, perhaps 10 times longer than it was wide, a geometry virtually unknown among natural asteroids or comets. Some estimates pushed the elongation even further, suggesting a needle or cigar shape that defied conventional formation mechanisms. The scientific community responded with a cascade of papers proposing natural explanations. Maybe it was a fragment of a planet torn apart by tidal forces. Maybe it was composed of unusual materials that didn't outgas visibly. Maybe the acceleration came from sublimating hydrogen ice, too faint to detect, but sufficient to provide thrust. Maybe. Each explanation solved one problem while creating others. Each hypothesis required special pleading, invoking conditions that were possible but uncommon, convenient but unconfirmed. And then Avi Loeb spoke up. Loeb, chair of Harvard's astronomy department, a scientist with an impressive publication record, and institutional credibility to burn, suggested publicly that Oumuamua might be artificial. He proposed it could be a light sailor, thin reflective sheet pushed by radiation pressure. Either a defunct piece of alien technology drifting through space, or more provocatively, an active probe from another civilization. The scientific establishment responded with what can only be described as fury. Loeb was accused of sensationalism, of damaging astronomy's reputation, of abandoning scientific rigor for publicity. The response was so intense, so visceral, that it raised its own questions about why the idea of extraterrestrial technology provoked such defensive reactions. 2 years later, in August 2019, another interstellar visitor arrived. This one, designated Chuai Borisov, behaved like a proper comet. It outgassed, normally displayed a visible tail, showed chemical compositions consistent with comets from our own solar system. The astronomy community breathed a collective sigh of relief. See, they seemed to say, interstellar objects are just like our objects. Our Myanmar was weird, but ultimately explicable. Everything's fine. We can return to normal. Except Atlas won't let us return to normal. In some ways, Atlas resembles Oumuamua more than it resembles Borisov. Both show non-standard acceleration that challenges simple gravitational models. Both display chemical or physical properties that sit awkwardly in our taxonomies. Both occupy the borderline territory between comet and rot, neither entirely one nor entirely the other. But Atlas might be substantially larger than Oumuamua if the size estimates are accurate. It shows that weird carbon dioxide-dominated outgassing that neither predecessor displayed, and those nickel signatures, that extreme polarization, those regular brightness variations all push it into new territory. Territory where our comfortable analogies break down. Where Atlas departs most significantly from its cousins is in the reaction it provoked. With Oumuamua, we're surprised, unsure how to interpret what we were seeing, willing to entertain multiple possibilities. With Borisov, we were relieved, eager to fit it into familiar categories. With Atlas, there's a sense that the scientific community has already decided what it wants to believe before all the evidence is in. After the Oumuamua controversy, after the accusations and counter-accusations, after watching a respected colleague get pilloried for asking uncomfortable questions, many astronomers seem to have made a collective, perhaps unconscious, decision to play it safe, to emphasize the natural explanations, to minimize the anomalies. This is what's called an over. When you get burned touching a hot stove, you might become overly cautious around all stoves, even ones that are clearly off. When the scientific community gets burned by public speculation about alien technology, it might become overly dismissive of any evidence that points in that direction, even when the evidence deserves serious consideration. The emotional memory of the Oumuamua debate may be influencing how Atlas is being interpreted right now, creating a bias toward conventional explanations that's just as unscientific as assuming everything weird must be artificial. Loeb himself has been cataloging the anomalies, arguing that our interpretive frameworks are systematically biased against recognizing technological signatures. He points out that we have one confirmed example of a civilization creating space objects, and we've been launching probes beyond our solar system for decades. The idea that another civilization might do the same isn't wild speculation. It's the application of the mediocrity principle, the notion that we're not special, that what happened here probably happened elsewhere too, if we find the evidence. For natural explanations insufficient, if we're invoking increasingly exotic conditions to maintain conventional interpretations. Maybe we're ignoring the simplest explanation one. That's only psychologically difficult because of what it implies. Historical context matters here. Throughout the history of astronomy, we've encountered objects that seemed weird, that defied explanation, that prompted speculation about unnatural origins. Pulsars, when first discovered, were jokingly called LGM's little green men, because the regular radio pulses seemed artificially precise. Quasars challenged our understanding of how much energy could be released from a given volume of space. Fast radio bursts still lack a completely satisfying explanation. In each case, we eventually found natural mechanisms that could produce the observations mechanisms that were often stranger and more interesting than artificial explanations would have been. But here's the thing. Just because we found natural explanations for previous anomalies doesn't guarantee that every anomaly has a natural explanation. That's the fallacy of induction, assuming that because X was true in the past, X must be true in the future. At some point, if we ever encounter actual evidence of extraterrestrial technology, it will look anomalous. It will defy our initial models. It will prompt exactly this kind of debate. And if we've trained ourselves to always dismiss the technological hypothesis, to always find some natural mechanism, no matter how contrived, we might miss the most important discovery in human history, simply because we'd rather be safely wrong than uncomfortably right. So where does that leave Atlas? Tumbling through space in the gap between certainty and speculation, observed by instruments that see fragments of the truth but never the whole picture. Which brings us to perhaps the most troubling aspect of this story: the missing data, the images that should exist but haven't been released, the gaps in the public record that might be innocent or might be something else. Let's examine what we're not seeing and why that might matter more than what we are. The missing data problem. Modern astronomy is a data-rich enterprise. We have telescopes in orbit, instruments on Mars, observatories scattered across every continent. When something interesting enters the inner solar system, dozens of instruments can point at it, capturing images across multiple wavelengths, building up a comprehensive picture of what we're dealing with. That's the theory anyway. The practice, particularly with Atlas, looks substantially different. The European Space Agency released a GIF from the CASIS camera aboard the ExoMars Trace Gas Orbiter. CASIS, designed to image the Martian surface in high resolution, was repurposed to capture Atlas during its relatively close approach to Mars. What did we get? A faint dot moving against the background of stars, a smudge barely distinguishable from noise, an image that confirmed Atlas existed and was where the orbital calculations said it should be, but revealed essentially nothing about its physical nature. For an object that was supposedly tens of kilometers across, passing within viewing range of a high-resolution camera, the lack of detail was frustrating. Either Atlas was much smaller than some estimates suggested, or it was oddly dark, or the camera wasn't pointed optimally, or some combination of factors conspired to give us the least informative image possible. Then there was the Perseverance rover, NASA's flagship Mars mission, equipped with navigation cameras that regularly scan the sky for dust, devils, and clouds. It called Atlas on October 4th as it appeared in the Martian sky. What did that image show? A streak, a line of light consistent with an object moving against the background stars, duration and direction matching Atlas's predicted path. Again, confirmation without revelation. We learned that Atlas was where it should be, moving as it should move, but nothing about what it actually was. These images were released, publicized, written up in press releases and news articles. They told us almost nothing. And maybe that's fine. Maybe these instruments simply weren't designed or positioned to give us better data. But here's where the story gets strange. Other instruments should have captured images, better images. And we haven't seen them. The Mars Reconnaissance Orbiter carries high-resolution imaging science, experiment capable of resolving features on the Martian surface as small as 1 meter across. When an interstellar object passes relatively nearby, you'd expect HIRIC to be tasked with capturing images, multiple images, tracking the object across several orbits to build up a comprehensive data set. Where are those images? The MAVEN spacecraft, studying Mars's upper atmosphere, has optical instruments that could have contributed observations. Where's that data? The Mars Odyssey orbiter, operational since 2001, has thermal imaging capabilities that might have detected heat signatures or assessed the object's surface temperature. Has that data been released? The official explanations, when they're offered at all, invoke sensitivity limits, scheduling conflicts, instrument constraints. HIRIC was designed for planetary surfaces, not fast-moving celestial objects. MAVEN's instruments are optimized for atmospheric science, not asteroid tracking. The data processing pipeline takes time, requires calibration, needs verification before release. And, oh by the way, there was that government shutdown in early 2025 that delayed numerous MICE's NASA operations and created a backlog of data processing tasks that's still being worked through. These explanations are plausible. They're reasonable. They might even be entirely true. But they exist in a context where the absence of data creates fertile ground for alternative narratives. When people expect to see something and don't, when institutions with a history of careful documentation suddenly have gaps in their records, suspicion fills the vacuum. There's a long history of claims that space agencies have either delayed or withheld anomalous images. The face on Mars, which turned out to be a mountain shaped by erosion and shadow, but was initially presented without sufficient explanation, trained a generation to mistrust NASA's image releases. Numerous conspiracy theories claim that photos from lunar missions, Mars rovers, and orbital surveys have been scrubbed or airbrushed to remove evidence of structures, artifacts, or other anomalies. Most of these claims are nonsense pattern matching or noise, seeing design in randomness. But the existence of mostly nonsense claims doesn't mean every claim is nonsense. And it doesn't mean agencies are always forthcoming with difficult data. The European Space Agency operates on a 6-month embargo for much of its raw data. Images and measurements are collected, processed internally, used by science teams, and only then released to the public archives. This is standard practice, designed to give researchers time to analyze data before releasing it to wider scrutiny. It's scientifically defensible and practically necessary. It also means there could be detailed images of Atlas sitting on ESA servers. Right now, images that won't be publicly available until mid-2026. Images that might answer questions we're currently debating in informational darkness. This creates what might be called the data vacuum effect. When the public knows observations should exist but can't access them, when the gap between what was observed and what's been released becomes large enough to notice, narratives rush in to fill the space. Some of those narratives are paranoid. Some are conspiratorial. Some posit cover-ups and secret knowledge and institutional lying. And some might actually be correct, or at least partially correct, Because the absence of evidence really is evidence of absence. When you expected that evidence to be present, consider the incentive structures at play. If Atlas is just a weird comet, releasing all available data immediately carries little risk and helps advance scientific understanding. If Atlas is something more ambiguous, something that might be artificial or that shows characteristics we can't explain, releasing that data creates problems. It invites intense scrutiny. It prompts questions the agency might not be ready to answer. It potentially reveals capabilities or limitations of our instruments that someone might prefer to keep private. It risks public panic or confusion if the implications are presented without proper context. None of this proves anything is being hidden, but it establishes that plausible motivations for selective release exist and that the gap between what's being observed and what's being shared is larger than routine scientific caution would explain. You're being asked to trust that the institutions studying Atlas are giving you the full picture, while simultaneously being told that much of the picture won't be available for review for months or years. That's a difficult ask, particularly given the stakes. Which brings us to the question that underlies this entire investigation. Why does it matter? If Atlas is natural, we learn something interesting about interstellar chemistry and move on. If it's artificial, well, that's the biggest news in human history. But beyond those outcomes, what's really at stake in how we interpret anomalous objects? What are we really arguing about when we debate whether Atlas is a comet or something else? Let's examine belief itself and what it costs us. Belief, skepticism, and the stakes. Ask yourself a simple question. Why does it matter whether Atlas is just a comet or something more? What changes about your life, your plans, your understanding of your place in the universe if the answer lands one way or the other? If Atlas is natural, if all those anomalies resolve into explicable chemistry and physics, we gain a rare window into the composition of another star system. We learn that planetary systems light years away can produce comets with different chemical signatures than ours, that the conditions of stellar formation vary more than we thought, that the universe is diverse in ways we're only beginning to catalogue. It's scientifically valuable, intellectually interesting, another data point in our expanding understanding of cosmic chemistry. We publish papers, we refine models, we move on to the next mystery. If Atlas is engineered, if we're actually looking at evidence of extraterrestrial technology, everything changes. This isn't hyperbole. The confirmation that intelligence exists elsewhere, that civilizations can arise and persist long enough to send probes between stars, that we're not alone in the universe. That realization would be the hinge on which human history pivots before and after. The way we think about our significance, our future, our responsibility to the cosmos, all of it would transform overnight. But those are the clean outcomes, the binary possibilities. The harder question is what happens in between, in the territory of uncertainty where we currently live, because right now, today, we don't know what Atlas is. We have data that points in multiple directions. We have institutions making claims we can't independently verify. We have gaps in information that might be innocent or might be suspicious. And we, the public, are being asked to decide what we believe without access to the full evidence. This is where psychological stakes enter the story. How humanity responds to potential first contact or to even ambiguous hints thereof. Who we are as a species. Do we approach the unknown with curiosity or fear? Do we demand transparency from our institutions or defer to their authority? Do we allow ourselves to entertain uncomfortable possibilities, or do we retreat into comfortable certainties? The Atlas event, regardless of its ultimate explanation, is a test of our civilizational maturity. There are institutional stakes here, too. Space agencies operate on public funding and political goodwill. Their budgets depend on maintaining credibility, on being seen as serious and scientific rather than speculative and sensational. If NASA or ESA announces they found evidence of alien technology and turns out to be wrong, the reputational damage would be immense. Funding could be cut, leadership could be replaced, future missions might be cancelled. The incentive structure pushes toward caution, toward certainty, toward only making claims you can definitively defend. This is understandable. It's human. It's also a bias that could cause us to miss or dismiss genuine anomalies, because acknowledging them carries professional risk. Then there's the risk of confirmation bias, the tendency to interpret new evidence as supporting what you already believe. If you want Atlas to be an alien probe, you'll emphasize the anomalies and downplay the conventional explanations. Every odd data point becomes evidence for your hypothesis. Every gap in the public record becomes proof of cover-up. You're not lying or being deliberately irrational. You're just human, filtering reality through the lens of your existing beliefs and desires. But there's an equal and opposite risk. Dismissal biased, the tendency to reject uncomfortable possibilities regardless of the evidence. If you're committed to the view that Atlas must be natural, you'll emphasize the conventional explanations and downplay the anomalies. Every odd data point becomes a minor puzzle rather than a major mystery. Every gap in the record becomes innocent. Delay rather than suspicious withholding. You're not being dishonest. You're just protecting yourself from the discomfort of paradigm shift. From the vertigo of having your fundamental assumptions about the universe challenged, both biases are traps. Both led away from truth. The question is whether you can hold multiple possibilities simultaneously, weighing them according to evidence rather than preference, updating your beliefs as new data arrives rather than clinging to initial positions. Regardless of what the universe shows you, this connects to a deeper philosophical question. Is belief in extraterrestrial probes a modern myth? A technological age replacement for gods and angels, a projection of our hopes and fears onto the cosmos? Or is it a rational inference from the available data? An application of Bayesian reasoning suggesting that given the age and size of the universe, given the number of potentially habitable planets, given our own existence as proof that intelligence can arise, the odds favor other civilizations existing and potentially sending emissaries into the void. The answer isn't obvious. Both positions have merit. Both can marshal evidence and logic in their defense. What's clear is that the question matters profoundly, not just for how we interpret Atlas, but for how we understand ourselves. Are we alone? If not, what does contact mean? if we're being visited or observed or simply brushed past by travelers from elsewhere, what responsibility does that place on us? These aren't abstract philosophical exercises. They're live questions with practical implications for how we allocate resources, how we plan for the future, how we conceive of humanity's role in the cosmic drama. And here's the uncomfortable truth. We're making these decisions, forming these beliefs, navigating these questions with incomplete information. The full data set exists. Some are images that could resolve ambiguities, spectroscopic data that could confirm or refute hypotheses, observational records that would let us see Atlas clearly rather than through the fog of selective release, an institutional caution. But we don't have access to that data. We're being asked to trust, to defer, to accept that those who know more than us are making the right calls about what to share and what to withhold. Maybe they are, maybe the agencies studying Atlas have excellent reasons for their communication, strategies. Maybe everything they're doing is scientifically sound and ethically defensible. But the structure of the situation, the asymmetry of information, the gap between what's known and what's shared, that structure itself creates the conditions for mistrust and speculation. When you treat the public as children who can't handle difficult truths, you shouldn't be surprised when the public starts assuming you're hiding something important. So we're left with uncertainty. A visitor from another star displaying properties that challenge our models observed by instruments whose data isn't fully available, interpreted by institutions with complex motivations. Atlas hangs in the sky, literally and metaphorically, a question mark written in rock or metal or something else entirely, and we're asked to decide what we believe about it. Without the information, we need to decide rationally. But Atlas isn't the only strange thing happening in space right now. Recent discoveries, fresh cosmic news may provide context or contrast or clues about how to interpret our interstellar visitor. In the next act, we shift focus to breaking space news, to anomalies and events that might be related or might be coincidental or might be something else entirely. Because sometimes understanding one mystery requires looking at all the other mysteries surrounding it. Sometimes the pattern only becomes visible when you step back far enough to see the whole sky. A black hole without a home. Imagine the most massive object you can. Neutron star, too light. Galactic core, too static. Now imagine something with the mass of several suns compressed into a region smaller than a city, warping space-time so severely that nothing, not even light, can escape its gravitational grip once the event horizon is crossed. You're imagining a black hole. Now set it adrift. Cut it loose from any galaxy, any stellar system, any gravitational anchor. Send it wandering through the void between stars, a cosmic predator hunting through darkness. In 2025, astronomers confirmed observations of what they're calling a rogue black holer. Stellar mass black hole, not bound to any obvious gravitational system, drifting through our galaxy like a ghost ship sailing between ports. This isn't entirely surprising in theory. Black holes form when massive stars collapse, and the galactic dynamics that govern stellar motion should occasionally fling a black hole out of its birth cluster, sending it on a lonely journey through space. What's surprising is detecting one. Black holes are famously invisible, only revealing themselves through their gravitational effects on nearby matter or through the radiation emitted by material falling into them. A rogue black hole with no companion star, no accretion disk, no convenient matter to consume and illuminate is essentially undetectable by conventional, means the detection came through gravitational microlensing technique that exploits Einstein's general relativity. When a massive object passes between us and a background star, the massive object's gravity bends the light from that star, creating a temporary brightening followed by a dimming as the alignment changes. By carefully measuring these brightness variations, astronomers can infer the mass and velocity of the intervening object. In this case, the microlensing signature suggested a dark, compact object with several solar masses moving through the galactic plane at velocities consistent with a stellar remnant rather than a normal star. The confirmation was significant because it validated theoretical predictions and gave us observational access to a population of objects that should be common but are rarely seen. Models suggest hundreds of millions of stellar mass black holes wander through the Milky Way remnants of ancient supernova, most of them completely invisible and undetectable unless they happen to pass directly in front of a background light. Source: we're monitoring DOT. We live in a galaxy filled with predatory gravitational wells. We can't see holes in space-time that would devour anything unfortunate enough to cross their event horizons. Now, here's where it gets interesting in the context of Atlas. Could a rogue black hole have influenced our interstellar visitor's trajectory? Could gravitational interactions with such an object explain some of the orbital peculiarities we're observing? At first glance, the idea seems plausible. Black holes are gravitational powerhouses. An encounter, even a distant one, would deflect an object's path, potentially explaining the trajectory that brought Atlas into our solar system from whatever stellar neighborhood birthed it. But the math doesn't quite work. Gravitational interactions are well understood, governed by equations we've tested to exquisite precision. For a black hole to significantly alter Atlas's trajectory without capturing it or accelerating it to even higher velocities would require an improbably fine-tuned encounter threading a needle in three-dimensional space across distances measured in light years. Possible? Yes, in the sense that nothing in physics forbids it. Likely? Not particularly. The universe contains countless ways for trajectories to be perturbed without invoking rogue black holes. Yet, there's something metaphorically resonant about these two anomalies existing simultaneously in our awareness. A black hole without a home and a comet without a clear origin, both wandering through space, both defying the tidy categories we prefer. Both remind us that the galaxy is more dynamic, more chaotic, more filled with drifting hazards and mysteries than the orderly diagrams in textbooks suggest. We imagine space as mostly empty, with occasional islands of matter and light. The reality is more unsettling. Space is filled with things we can't see: mass, objects moving through darkness, ancient remnants of stellar death sailing between the stars we can observe. The existence of wandering black holes also raises uncomfortable questions about what else might be drifting out there. If stellar remnants can be ejected from their birth systems, what about planetary remnants? What about objects that were never gravitationally bound to begin with? What about things that were placed on trajectories deliberately rather than by random gravitational perturbations? The census of interstellar space is almost completely unknown. We see the objects that emit or reflect light toward us. Everything else, the dark matter, in the colloquial rather than cosmological sense, remains invisible until it happens to pass close enough to our instruments to be detected. This connects to a larger theme running through our investigation. We're discovering that space isn't the quiet, predictable environment we thought it was. The smooth galactic dynamics we assumed, where everything orbits in orderly fashion around gravitational centers, is complicated by rogues and wanderers, by objects that don't follow the script. And if the script is wrong about black holes, if it's wrong about the number and nature of objects drifting between stars, what else might it be wrong about? The timing is curious, too. Here we are in 2025, tracking an anomalous interstellar object through our solar system and simultaneously confirming the existence of rogue black holes wandering our galaxy. These discoveries aren't necessarily related. Astronomy is an active field. New findings emerge constantly. But there's something about the convergence of anomalies, the clustering of strange observations in a brief window of time, that makes pattern-seeking minds wonder if there's a connection we're not seeing. Correlation isn't causation, but it's also sometimes a clue pointing toward deeper structures we haven't recognized yet. And black holes aren't the only cosmic wound demanding our attention right now. While we've been tracking objects drifting through the galaxy, our own star has developed an injury that affects everything we're trying to observe. Let's turn our attention to the sun and to a hole that might be interfering with how clearly we can see the truth. The sun's colossal wound. The sun isn't smooth. We imagine it as a perfect sphere of fusion and light, consistent and predictable, the cosmic engine that powers our planetary system. The reality revealed by solar telescopes is more violent. The sun's surface writhes with convection cells and magnetic tangles. Sunspots bloom and fade. Prominences arc thousands of kilometers into space, and occasionally the sun opens a wound. Coronal holes are exactly what they sound like, gaps in the sun's outer atmosphere, where the magnetic field lines don't loop back to the surface, but instead stream outward into space. These aren't holes in the physical sense, not voids where matter is missing, but regions where the plasma is cooler and less dense than the surrounding corona, appearing dark in extreme. Ultraviolet images. More importantly, they're regions where the solar wind escapes unimpeded, accelerating to speeds of up to 800 kilometers per second, carrying charged particles and magnetic fields deep into the solar system. In October 2025, solar observatories detected a massive coronal hole facing Earth, one of the largest in recent years. The hole stretched across a significant fraction of the sun's visible disk, a dark patch in the churning bright surface, like a cosmic wound that wouldn't heal. Forecasters predicted strong solar wind streams would reach Earth within days, potentially triggering geomagnetic storms, disrupting satellite operations, creating auroras at unusually low latitudes, and generally making the electromagnetic environment of near-Earth space more chaotic than normal. For most people, coronal holes are interesting primarily because they create beautiful auroras. The charged particles streaming from the sun interact with Earth's magnetic field and atmosphere, exciting atoms and molecules into emitting light, painting the sky with curtains of green and red and purple. It's a spectacular show, one of nature's most impressive light displays, and it draws photographers and tourists to high-latitude locations whenever strong solar activity is predicted. But for astronomers trying to make precise observations of faint objects, solar storms are a nightmare. The flood of charged particles interferes with radio observations, creating noise that drowns out faint signals. The magnetic field fluctuations affect spacecraft operations, potentially degrading the quality of images from orbital telescopes. Even ground-based optical telescopes can be affected as increased ionization in Earth's upper atmosphere distorts the light passing through. When the sun is actively wounded, when coronal holes are blasting plasma toward Earth, our ability to see clearly into space diminishes. Now consider the timing. Atlas reached perihelion, its closest solar approach, on October 30th, 2025. That's the moment when telescopes should have been gathering the most detailed data. When the object was brightest and closest and most accessible to observation, and that's precisely when a massive coronal hole was facing Earth, when the solar wind was at its strongest, when the electromagnetic environment was most disrupted. Coincidence? Almost certainly. Solar activity follows its own cycles, independent of what asteroids or comets happen to be passing through. Coronal holes develop according to magnetic dynamics we don't fully control or predict. The overlap is just bad luck, an unfortunate alignment of observational windows and solar behavior. Or is it? Here's where we have to be careful about the narratives we construct. It's very easy to see patterns where none exists, to interpret coincidences as conspiracies, to imagine that the universe or some agency within it is deliberately timing things to interfere with observation. That's almost certainly not what's happening, but the effect remains regardless of the cause. During the crucial period when Atlas was best positioned for detailed study, our instruments were operating in a degraded environment, fighting through solar noise to capture data. Any marginal signals, any subtle anomalies, any fine details that might have resolved questions about the object's nature, those observations would have been harder to make, easier to miss, more likely to be buried in noise. The metaphor is irresistible. A hole in the sun, a wound in our star creating a smokescreen during the very window when we needed clarity. It reads like a thriller screenplay, like something designed to maximize uncertainty. And maybe that's all it is, a coincidence that feels meaningful because humans are pattern-matching machines who see design in randomness. But it's also true that if you wanted to observe something without being clearly observed, if you wanted to pass through a stellar system while remaining ambiguous, timing your arrival during a period of high solar activity would be strategically sound. You'd benefit from the degraded observation, from the noise masking your signals, from the reduced clarity of the instruments tracking you. This is the problem with uncertainty. Once you're in it, every data point can be interpreted multiple ways. The coronal hole is just weather, solar dynamics following their own patterns. Or the coronal hole is a smokescreen, an interference pattern that benefits an object trying to remain ambiguous. Both explanations fit the facts. Neither can be definitively proven or disproven. With the information available, we're left once again in the territory between knowing and speculating, and the cosmic strangeness doesn't stop with holes in the sun. While we've been watching objects drift and our star bleed plasma into space, cosmologists have been reconsidering the ultimate fate of everything. Is the universe expanding forever, or could it be heading toward a collapse? Let's examine how. Beliefs about cosmic destiny might be influencing how we interpret present anomalies. The crunch clock starts ticking. The universe is expanding. Every galaxy we can see is moving away from every other galaxy, space itself stretching like the surface of an inflating balloon. This has been confirmed observational fact since Edwin Hubble's work in the 1920s, refined through decades of increasingly precise measurements. The expansion is accelerating, driven by something we call dark energy, a mysterious component of the universe that acts like anti-gravity on cosmic scales, pushing space apart faster and faster. According to the Standard Model, this expansion will continue forever. Galaxies receding until they vanish beyond our cosmological horizon. Stars burning out one by one. The universe growing cold and dark and empty in a heat death that takes trillions upon trillions of years. That's been the consensus, the comfortable nightmare, if you will, a fate so distant and impersonal that it barely registers as a threat. We have time, inconceivable amounts of time. Whatever else happens to humanity, to Earth, to our corner of space, the universe itself will persist for eons, except in 2025. Certain cosmological papers began questioning this assumption. New analyses of dark energy behavior, subtle patterns in cosmic microwave background data, refined models of how the universe's expansion rate has changed over time, more pointed toward a possibility that had been dismissed as unlikely. What if dark energy isn't constant? What if it's weakening or changing character, or heading toward a phase transition that would flip the expansion into contraction? What if the universe's destiny isn't heat death, but the big cruncher gravitational collapse that would eventually pull everything back together? Galaxies colliding, space compressing, matter and energy crushed into a singular point in a reversal of the Big Bang. The papers were tentative, heavily qualified, careful to note that the evidence was far from conclusive. The odds still favored eternal expansion. But the possibility of contraction, once considered virtually zero, was now being assigned small but non-negligible probability, maybe 1%, maybe 5%, enough that serious cosmologists had to consider it. Run simulations. Think about what observational signatures would confirm or refute the hypothesis. Why does this matter for our investigation of Atlas? Because cosmological narratives shape how we interpret local events. When the ultimate fate of the universe feels settled, when we're confident about the cosmic story arc, anomalies get slotted into that stable framework. This comet is weird, but the universe is stable, so the weirdness must be explicable within our existing models. But when the cosmic story itself becomes unstable, when the ending gets rewritten, suddenly everything feels less certain. If we were wrong about the universe's fate, what else might we be wrong about? If the framework itself is shifting, maybe those anomalies deserve more attention than we've been giving them. There's also a psychological dimension here. Doom narratives, predictions of cosmic endings tend to intensify during periods of cultural anxiety or paradigm shift. Medieval Europe was obsessed with apocalypse prophecies during times of plague and social upheaval. The Cold War generated countless scenarios of nuclear winter and societal collapse. And now, in an era of climate disruption, political instability, and rapid technological change, we're seeing renewed interest in cosmic doom scenarios. In endings both near and far, the Big Crunch narrative fits this pattern. It's a cosmic reset. But an ending that's also a beginning, a collapse that might lead to a new Big Bang and a new universe. It's psychologically satisfying in a way that heat death isn't. Heat death is just entropy winning, everything slowly winding down into nothing. The crunch implies purpose, cycle, the possibility that universes are born and die and are reborn in an eternal pattern. It's mythology dressed in mathematical clothing, and it appeals to something deep in human psychology that wants to believe. Existence has structure and meaning beyond simple thermodynamics. So when papers appear suggesting the universe might crunch, rather than expand forever, they're not just presenting dry technical results. They're offering a new narrative, a different way of thinking about cosmic destiny. And that narrative primes us to interpret present events through a particular lens. If the universe itself is heading toward collapse, toward a gathering together of everything that's been flying apart, maybe interstellar visitors like Atlas aren't random wanderers, but part of some larger pattern, some cosmic choreography. Don't yet understand. This is speculative territory, obviously. The connection between cosmological models and interstellar objects is tenuous at best. But narratives don't have to be logically rigorous to be psychologically powerful. When you believe the universe is on a path toward fundamental transformation, you start seeing signs of that transformation everywhere. Every anomaly becomes a herald. Every mystery becomes a clue. The framework shifts, and with it, your interpretation of everything within the framework. And here's the uncomfortable truth. Scientists are human. They're not immune to narrative influence. When the broader culture is focused on endings and transformations, when cosmological models are in flux, when the old certainties are being questioned, that atmosphere affects how researchers interpret their data, what hypotheses they consider plausible, what anomalies they think deserve investigation versus dismissal. Science isn't a pure objective process isolated from human psychology. It's a human activity conducted by humans with human biases and human narrative drives. And those drives inevitably influence the work. So the Big Crunch papers, regardless of their ultimate validity, change the interpretive environment. They make it easier to think big thoughts, to entertain cosmic-scale possibilities, to wonder if the anomalies we're seeing are connected to larger patterns. They don't prove anything about Atlas, but they change the atmosphere in which Atlas is being interpreted. And sometimes atmosphere matters as much as evidence. But let's bring the focus back from cosmic destiny to more immediate concerns. While astronomers debate the fate of the universe, something more prosaic but equally disruptive has been happening in our orbital space. Satellites are falling regularly, quietly, and their rain of fire might be masking something important. Starlink's quiet rain of fire. Every day, somewhere above your head, a satellite dies. not metaphorically, literally. Metal and silicon and solar panels heating to thousands of degrees as they slam into Earth's atmosphere, ablating away, breaking apart, raining down as microscopic debris or occasionally larger fragments that survive to impact the surface. A Smithsonian astrophysicist recently estimated that 1 to 2 Starlink satellites burn up or fall back to Earth daily. Not miles lately, that's hundreds of objects per year from a single mega-constellation vaporizing as they descend. The reason is simple physics. Low Earth orbit isn't empty. There's residual atmosphere even at altitudes of several hundred kilometers, enough to create tiny amounts of drag on satellites. Over time, the drag slows the satellites, lowering their orbits, until eventually they dip into denser atmosphere and can't maintain altitude anymore. Orbital decay is inevitable. Every satellite launched will eventually fall unless constantly boosted to maintain its orbit. 4 small satellites without substantial fuel reserves. The operational lifetime might be only a few years before atmospheric drag wins and they begin their final descent. Starlink. SpaceX's mega constellation designed to provide global internet coverage consists of thousands of satellites in low orbit. The plan calls for tens of thousands of entry-in networks so dense that from any point on Earth, multiple satellites are visible above the horizon. This requires operating in low orbits where atmospheric drag is significant, which means satellites must be regularly replaced as they decay and burn up. Hence, the daily rain of fire, a steady stream of dying hardware vaporizing over our heads. Mostly unnoticed because the individual events are too small and too common to make news. But here's what this does to the observational environment. It adds clutter. Thousands of satellites reflecting sunlight, interfering with telescope observations, creating streaks across astronomical images that have to be digitally removed. It increases false positives objects that appear briefly in sky surveys but turn out to be satellites or satellite debris rather than asteroids or comets. It makes the already difficult task of tracking small objects through space even harder because you have to distinguish genuine celestial phenomena from the growing cloud of human-made hardware cluttering near-Earth space. For observers trying to study something like Atlas, this matters. When you're analyzing faint objects, when you're looking for subtle variations in brightness or trajectory, when you're trying to confirm whether an observation is real or artifact, the presence of thousands of artificial objects in your field of view complicates everything. Every mysterious signal could be a satellite. Every unexplained flash could be debris catching sunlight at an unusual angle. The noise floor rises, and with it the difficulty of extracting genuine signals from background. There's also a more speculative possibility worth considering. Could the proliferation of satellite activity provide cover for detecting or masking other anomalies? If you wanted to observe Earth without being clearly identified, if you wanted to pass through near-Earth space while maintaining plausible deniability, blending in with the thousands of artificial objects already present would be strategically sound. Every telescope that sees you could reasonably assume you're just another satellite, just more orbital debris, just part of the growing clutter that everyone's learned to filter out. The camouflage isn't deliberate on your part. PAEDs provided by humanity's own technological infrastructure, by the constellation of hardware we've surrounded ourselves with. This connects to a broader theme about signal and noise. about how increasing complexity makes it harder to see clearly. The more satellites we launch, the more difficult astronomy becomes. The more space junk accumulates in orbit, the harder it is to distinguish significant observations from insignificant ones. Creating our own fog, surrounding ourselves with a technological haze that obscures the very cosmos we're trying to study. And anything that wants to remain hidden or ambiguous or unnoticed benefits from that haze. The irony is thick. We launch satellites to improve communication and observation, to give us better tools for studying the universe. But in doing so, we degrade the environment those observations happen in, making it harder to see faint objects, harder to track anomalies, harder to know whether what we're detecting is significant or just another piece of falling hardware catching sunlight. As it burns, progress creates its own obstacles. The better our technology gets, the more that technology interferes with itself. And there's no easy solution. The satellites serve purposes. People value internet access, weather monitoring, communications, infrastructure all depend on the orbital constellation. Arguing to reduce the number of satellites means arguing to give up capabilities and services that millions of people rely on. So the constellation will grow, the clutter will increase, and the observational environment will continue to degrade. That's the trajectory we're on. And barring some major policy shift or technological breakthrough, it's the trajectory we'll stay on. Which brings us to perhaps the most puzzling aspect of the Atlas story. The silence, the gaps in communication, the sense that institutions which should be sharing information are holding back. Why are the agencies so quiet when odd things appear? What's the logic or the fear behind selective disclosure? Let's examine the silence itself and what it might tell us. The silence before disclosure. Silence is a kind of information. When you expect to hear something and don't. When institutions that normally communicate regularly suddenly go quiet. When the absence of statements becomes more noticeable than the presence of them, you're receiving a signal, even if it's a negative one. The silence around Atlas, the gaps between observations and announcements. The careful vetting of every public release, all of it communicates something, even if we're not sure exactly what. Space agencies operate under constraints most people don't think about. Every image released to the public has to be reviewed, calibrated, verified. Every statement about observations has to be precise, defensible, unlikely to be contradicted by future data. This isn't censorship or conspiracy. It's the normal caution of institutions that understand their credibility depends on accuracy. If NASA announces a discovery that later turns out to be instrumental error or misinterpretation, the damage to their reputation can be severe and long-lasting. So they check, they double-check, they wait until they're confident before saying anything publicly. This creates a temporal gap, delay between observation and announcement, that's usually measured in weeks or months. For routine observations, this barely matters. So what if the press release about some distant galaxy comes 6 months after the telescope captured the image? The galaxy isn't going anywhere, but 4 time-sensitive events, 4 objects passing through our solar system. On schedules measured in days and weeks, that delay becomes significant. By the time the agency is ready to make a statement, the event has often passed, the object has moved on, and the public is left wondering why they weren't informed earlier. The pattern is visible across multiple recent events. when new exoplanets are discovered through gravitational wave detection or transit methods, months often pass before the discovery is announced. When interesting signals are detected by radio telescopes, extensive verification happens internally before anyone outside the research team is informed. When orbital missions capture unusual images, those images go through processing and analysis, pipelines that can take a year or more before public release. This is standard operating procedure, not specific to Atlas or any particular mission. But standard procedure feels different when the observation might be extraordinary, when the delay affects data that could answer fundamental questions about our place in the universe, when the gap between seeing and sharing creates space for speculation and alternative narratives. The routine caution starts looking like something else. It starts looking like deliberate withholding, like information control, like an institution deciding what the public gets to know and when. This is where institutional incentives create problems. Agencies want to control their narratives. They want to make announcements on their own schedule, in their own words, with their own framing. Leaks are bad. Premature releases are bad. Speculation before verification is bad. All of this makes sense from the agency's perspective, but from the public's perspective, it looks like secrecy. It looks like decisions being made behind closed doors about what information is suitable for general consumption. And that appearance, regardless of whether it reflects reality, damages trust. There's historical precedent for agencies delaying or initially withholding anomalous findings. The famous face on Mars captured by Viking orbiter in 1976 was initially presented in a press release that emphasized its artificial appearance before later. Releases provided context about how lighting and resolution affected interpretation. The WOW signal detected in 1977 by SETI. Researchers wasn't publicly discussed in detail for years, despite being one of the most intriguing radio observations ever made. The dimming of Tabby's star, which some speculated might indicate an alien megastructure, was known to researchers well before it became public knowledge through data release. In each case, there were reasonable explanations for the delay. Scientists wanted to rule out instrumental error. They wanted to gather more data. They wanted to avoid making claims they couldn't defend. But the effect was the same. The public learned about potentially significant observations long after. They occurred through channels that felt more like PR management than transparent scientific communication. And each instance reinforced the sense that institutions were gatekeeping information, deciding what questions were acceptable to ask publicly and which should remain in private discussions among credentialed experts. Apply this pattern to Atlas. The object was discovered in July. It's now late October. We've seen a handful of images, mostly showing faint dots or streaks. We've read press releases emphasizing the natural comet explanation, downplaying anomalies, reassuring us that everything is normal and expected. We haven't seen higher resolution images from instruments that should have captured them. We haven't had access to the raw spectroscopic data that would let independent researchers verify the chemical claims. We're being asked to trust that the institutions studying Atlas are telling us everything important, while simultaneously being aware that their history suggests they often don't. This creates what might be called the silence window, the gap between observation and disclosure, where narrative management happens. During this window, the agency controls the story. They decide what gets emphasized and what gets buried in technical appendices. They frame the discovery in language that shapes how the public interprets it. And they do all of this behind closed doors, in internal meetings and peer review processes that the public never sees. By the time we get the official story, the narrative has already been constructed, the interpretation decided, the acceptable range of speculation defined. Is this conspiracy? Not in the sense of deliberate, malicious cover-up, but it is information control, narrative management, institutional self, and it creates the conditions where conspiracy theories flourish. Because when people know they're not getting the full story, they fill the gaps with their own narratives, often more dramatic and less plausible than the truth would be if it was simply shared openly. Atlas sits at the center of multiple weird signals, multiple cosmic anomalies that may or may not be related. Rogue black holes wandering the galaxy, holes in the sun disrupting observations, cosmological models in flux, satellites falling like rain. Each of these could be independent, unconnected developments. Or there could be pieces of a larger pattern we're not seeing because the data is scattered. The release is delayed. The narrative fragmented by institutional caution and communication strategies. What we know is that an object from another star system is passing through ours right now, displaying properties that challenge our models, and the institutions studying it are being careful about what they share and when. The silence might mean nothing, or it might mean everything. We won't know until the window closes, until the data is finally released, until we can see for ourselves what Atlas actually is. Until then, we're left with gaps and guesses, watching the sky and wondering what's being seen but not shared. And speaking of the sky, let's shift our attention to the calendar itself. Because while all this strangeness unfolds, celestial events march forward on schedules set by orbital mechanics and cosmic timing. These events, these spectacles, might be distractions, or they might be opportunities. They might hide what we need to see or reveal what's been hidden. Either way, they're coming. Mark your calendars. The show is about to begin. The cold moon rises December 4th. The moon has many names, inherited from cultures that tracked its phases as calendar and clock. The full cold moon rises on December 4th, 2025. The name given by colonial Americans following indigenous traditions that associated this particular full moon with the onset of deep winter, with cold nights and frozen ground, with the year drawing toward its darkest point before the solstice promises eventual return of light. There's something primal about full moons. They've triggered human behavior for as long as humans have existed, marking times for hunting, for planting, for ritual and celebration. Modern people like to think we're beyond such influences, that electric lights and digital calendars have freed us from lunar tyranny, but hospital emergency rooms still report increased activity during full moons. Police departments note changes in core patterns. Sleep studies show measurable effects on human circadian rhythms, even when subjects can't see the moon. We're still animals, still influenced by the ancient rhythms our ancestors evolved under, even if we pretend otherwise. The cold moon will be visible globally, weather permitting, rising in the east as the sun sets in the west, climbing to its highest point around midnight, illuminating the landscape with that peculiar, colorless brightness. That's bright enough to read by, but not quite bright enough to see color. It's a liminal light caught between day and night, making the familiar world strange and the strange world visible. From a strictly astronomical perspective, this full moon is unremarkable. It's not a supermoon, not unusually close or large or bright. It's just the moon being the moon, completing another orbit, reflecting another face of sunlight toward Earth. But symbolically, culturally, psychologically, it matters. People will go outside to look at it. Photographers will capture it rising over landscapes and cityscapes. Social media will fill with moon images, each one slightly different, each one attempting to capture the uncapturable feeling of standing under that light and feeling small and connected and ancient all at once. Now, here's a speculative overlay. What if anomalies like Atlas are timed deliberately or coincidentally to pass when public attention is fixed elsewhere? The full moon is a natural spotlight, a celestial event that draws millions of eyes upward. When people are looking at the moon, they're not looking at other things. When telescopes are pointed at the moon or dealing with its brightness drowning out faint objects, they're not tracking anomalies in other parts of the sky. The moon, in effect, creates a blind spot, a moment of collective attention that could mask other events happening simultaneously. This isn't to suggest some cosmic conspiracy where alien visitors coordinate their arrivals with lunar phases. That's absurd. But it is to note that when human attention is concentrated in one direction, opportunities arise in other directions. Magicians understand this principle. Misdirection is the core of the craft. Get the audience looking at your right hand. They'll miss what your left hand is doing. Get the audience looking at the moon. They'll miss what's moving in the darker sky beyond it. The cold moon also carries symbolic weight that affects how we interpret events around its timing. Cold suggests closure, dormancy, the end of a cycle. December is when things die back, when growth stops, when the world turns inward. If strange events clustered around this timing, if disclosures or discoveries happen in early December, they'll be interpreted through that symbolic lens: endings rather than beginnings, closure rather than opening. The narrative frame shifts based on when things are revealed, even if the timing is purely coincidental. And maybe it is purely coincidental. Maybe lunar phases and interstellar visitors have nothing to do with each other. Maybe the cold moon is just the moon and Atlas is just passing through, and any connection between them is pattern matching on randomness. But humans are storytelling. Animals. We can't help but see narratives in events, connections in coincidences, meaning in timing. The moon rises, the visitor passes, and somewhere in the overlap, we construct a story that makes sense to us, even if it doesn't make sense to the universe. The important thing is to notice what you're noticing. When the cold moon rises, when your attention goes skyward, ask yourself what else is happening. What other objects are moving through space? What data is being released or withheld? What announcements are being made or delayed? The moon is beautiful, worth watching, worth photographing and celebrating. But don't let its beauty blind you to everything else the sky contains. Sometimes spectacle is just spectacle, and sometimes it's cover for something you'd otherwise notice. Speaking of spectacle, the cold moon is just the opening act. A supermoon is coming, bigger and brighter, guaranteed to dominate headlines and social feeds. Let's examine how the biggest lunar show of 2025 might be shaping what we see and what we miss. The supermoon of 2025, early November. A supermoon sounds dramatic, like something out of comic books or disaster movies. The reality is more subtle, but still genuinely impressive. A supermoon occurs when the full moon coincides with perigee, point in the moon's elliptical orbit where it passes closest to Earth. The moon's orbit isn't circular, it's an ellipse, which means sometimes the moon is about 50,000 kilometers farther from Earth than at other times. When the full moon happens at perigee, it appears about 14% larger and 30% brighter than when it's at apogee, the farthest point. That's enough to be visually noticeable if you're paying attention, especially when the supermoon rises near the horizon, where atmospheric effects can make it look even larger through an optical illusion. The biggest supermoon of 2025 occurs in early November, either the 3rd or 4th, depending on how you measure the exact moment of perigee versus the moment of full illumination. For casual observers, the distinction doesn't matter. What matters is that for several nights, the moon will dominate the night sky, bright enough to cast strong shadows, beautiful enough to stop people in their tracks, attention-grabbing enough to become a cultural moment rather than just an astronomical event. And that's where it gets interesting from our perspective. Supermoons generate massive public engagement. They're accessible astronomy, requiring no equipment beyond eyes and curiosity. News outlets cover them, weather forecasters mention them. Social media explodes with supermoon photos taken from every possible location and angle. For a few nights, millions of people who normally never think about celestial mechanics become amateur moon watchers, stepping outside to look up, sharing what they see, participating in a collective astronomical experience. This is wonderful. Anything that gets people interested in space, that makes them look up and wonder, that connects them to the cosmos beyond their immediate concerns, that's a net positive for human civilization. But it's also a massive redirection of attention. When everyone's looking at the moon, when telescopes are dealing with its brightness, when the cultural conversation is dominated by supermoon imagery, other things can pass relatively unnoticed. Atlas's closest to Earth approach happens in late October, just before the November supermoon. The timing means that as Atlas is moving through the most observable part of its trajectory, public attention is about to be captured by a lunar spectacle. Professional astronomers will still track Atlas. Of course, they're not distracted by pretty moons, but public attention, media coverage, the broader conversation about what's happening in space, all of that shifts toward the more accessible, more visually dramatic event. Atlas becomes background noise, if it's mentioned at all, overshadowed by the supermoon's mainstream appeal. There's a historical pattern here worth noting. Major announcements sometimes get released when public attention is elsewhere. Governments announce unpopular policies on Friday afternoons before holiday weekends. Corporations release bad financial news after markets close. It's not necessarily conspiracy, it's just strategic communication. choosing timing that minimizes negative attention or allows the message to be processed without immediate intense scrutiny. Could the same principle apply to space anomalies? Could timing disclosures or non-disclosures around major celestial events be a deliberate strategy for managing public reaction? Maybe. Or maybe the timing is genuinely coincidental, the result of orbital mechanics and observational windows having nothing to do with communication strategy, but the effect remains. When the supermoon dominates the cultural conversation about space, anomalies like Atlas fade into background. Questions that might be asked loudly in a quieter news environment get asked softly or not at all, drowned out by supermoon excitement. And here's the psychological dimension. Supermoons are comforting in a strange way. They're predictable, expected, part of the regular rhythm of celestial mechanics. They remind us that some things about the universe are stable, that orbital dynamics follow comprehensible rules, that we can predict and prepare for these events with perfect accuracy. In a time of cosmic uncertainty, when interstellar visitors and rogue black holes and cosmological doom scenarios are circulating through scientific discourse, the supermoon offers reassurance. Look, it says, the universe still works the way you learned in school. The moon still orbits Earth. Perigee and apogee still happen on schedule. Not everything is strange. That reassurance, that return to the familiar, might be exactly what people need psychologically, or it might be what prevents them from grappling with genuinely strange developments. When you're offered comfort, when spectacle provides an easy focus point, it's tempting to accept that and ignore the harder, more unsettling questions lurking just outside the spotlight's reach. The supermoon is beautiful, but beauty can be a trap, something that keeps you looking in one direction while other directions remain unexplored. So when the supermoon rises in November, when the sky is dominated by that enlarged, brightened disk, remember to look around it. Check what else is visible. Ask what data is being released or held back. Notice whether announcements happen during the supermoon window or are strategically delayed until after the spectacle passes. The moon deserves your attention, but it shouldn't monopolize it. The sky is larger than the brightest object within it, and sometimes the most important things are happening in the darker spaces we'd rather not examine. Speaking of things streaking through darkness, the supermoon isn't the only celestial show. Scheduled for the coming months, meteor showers are approaching. Annual events that paint the sky with fire and have their own ways of capturing attention and perhaps concealing what we should be noticing. Let's turn to the southern turrets. And what happens when the sky fills with streaks of light? The southern turrets aren't the most spectacular meteor shower. Peak rates are typically only 5 to 10 meteors per hour. Modest compared to showers like the Perseids or Geminids that can produce dozens or even hundreds of meteors per hour during their peaks. But the Taurids have a reputation among meteor enthusiasts for producing fireballs, unusually bright meteors that can briefly outshine even the brightest stars, occasionally leaving persistent trains of glowing ionized gas that linger for seconds after the meteor itself has vanished. The shower is active from late September through late November, with peak activity typically occurring in early November, overlapping with that supermoon window we just discussed. So during the same period, when the moon is unusually bright and public attention is skyward, the sky is also being regularly streaked by meteors. Natural fireworks that add to the spectacle and to the overall sense that a lot is happening above our heads. From one perspective, this is pure coincidence. Earth's orbit is fixed. Comet Inc.'s debris stream is where it is. The moon's perigee happens when it happens. These are independent phenomena determined by gravitational mechanics that care nothing for human observation or interpretation. The timing overlap is just the universe being busy in multiple ways simultaneously. From another perspective, the overlap creates noise. When you're trying to track specific objects through space, when you're looking for anomalies or unusual trajectories, a sky full of meteors complicates the task. Every streak of light has to be identified. Is it a Taurid meteor? Is it a satellite? Is it space debris? Is it something else? The more natural phenomena are occurring, the harder it becomes to distinguish signal from noise, the genuine anomaly from the expected event. And here's a speculative question worth considering. Could fragments from interstellar objects be misclassified as meteors? Atlas is outgassing, shedding material as it passes through the solar system. That material forms a tail, a cloud of particles following the comet's trajectory. If Earth happened to pass through that particle stream, if pieces of interstellar matter entered our atmosphere, would we recognize them as distinct from the annual meteor showers we expect? Or would we assume they were just part of the Taurids, just more debris from Comet Inc., and never investigate further? The chemistry should reveal the difference. Meteor spectroscopy can identify composition and material from an interstellar. Objects should show chemical signatures distinct from solar system comets. But that assumes someone captures a spectrum of the specific meteor in question, that the observation happens during the brief seconds while the meteor is visible, that someone notices something unusual enough to warrant detailed analysis. 4. The vast majority of meteors, we see a streak, maybe photograph it, and move on. The detailed spectroscopy happens only for the most interesting or well-observed cases. This creates a pattern blending effect. High meteor activity provides cover, a background of expected events that might mask unexpected ones. If you wanted to study Earth without being clearly identified, if you were shedding material that might enter Earth's atmosphere, timing that process to coincide with a major meteor shower would be strategically sound. Your debris gets mixed with expected debris. Your signals get lost in expected signals, and human observers, seeing what they expect to see, classify everything as part of the known phenomenon without looking closer. Again, this is speculation. There's no evidence that Atlas fragments are entering Earth's atmosphere. There's no proof that anything unusual is hiding among the Taurids. But the structural possibility exists. The theoretical window where misidentification could occur. And that window is worth noting because it affects how confidently we can claim to know what we're observing. There's also the simple fact that meteor showers draw eyes upward. Like the supermoon, like any celestial spectacle, they focus attention in specific directions at specific times. When people are outside watching for Taurid fireballs, they're engaged with the sky in ways they normally aren't. They're noticing things, pointing at things, photographing things. But their attention is directed toward the meteors, toward the expected show. Other objects moving through the sky might be visible, but unnoticed background to the foreground. Performance. The Taurids also carry a certain mythology in astronomical circles. Some researchers have suggested that the Taurid complex, the broad stream of debris associated with Comet Encke, might contain larger fragments, kilometer-sized rocks that pose potential impact hazards to Earth. These claims are controversial and not widely accepted, but they add an undercurrent of threat to what's otherwise a beautiful annual event. When you watch Taurid meteors, you're watching small particles that pose no danger. But in the back of your mind might be the question of whether something larger is out there, hidden in the same debris stream, potentially on a collision course. Atlas isn't part of the Taurid complex. Its origin is interstellar, completely unrelated to Comet Encke. But the psychological association, the connection between things in the sky and potential threat, creates a framework where anomalous objects get interpreted through a lens of danger. The Taurids remind us that space contains hazards. Atlas, arriving from interstellar space with unusual properties, gets slotted into that hazard category even though it poses no collision risk. The narratives blend, not because they're factually related, but because they activate similar psychological responses. So when the southern Taurids peak in early November, when the sky fills with streaks and fireballs, pay attention not just to the meteors, but to what else might be moving. Notice whether unusual objects get reported and dismissed. Ask whether the pattern blending is innocent or convenient. The Taurids are worth watching. They're a genuine natural wonder, a reminder that we live inside a dynamic system where matter is constantly in motion. But don't let the expected show blind you to unexpected. Performance is happening in other parts of the sky, and the Taurids are just the beginning. More meteor showers, a Kaminkka cascade of celestial fireworks that will light up the sky through November and December. Let's examine how this clustering of spectacles might be shaping what we see and what remains hidden in the spaces between the streaks. The Leonids, Geminids, and Ursids cascade of showers. The sky in late 2025 is busy, not just with Atlas, not just with supermoons and coronal holes, but with a regular programming of meteor showers. 3 major displays arriving in quick succession, like a coordinated performance scheduled by the universe itself. The Leonids arrive on November 17th and 18th. Debris from Comet Tempel-Tuttle, creating meteors that appear to radiate from the constellation Leo. The Leonids are famous for occasionally producing meteor storms, events where thousands of meteors per hour paint the sky. Those storms happen only during specific years when Earth passes through particularly dense regions of the debris stream. 2025 isn't a storm year. The Leonids will be modest, maybe 10 to 15 meteors per hour at peak, visible in the pre-dawn hours when Leo is highest in the sky. Then come the Geminids on December 13th and 14th, generally considered the most reliable and impressive meteor shower of the year. The Geminids are unusual because they originate not from a comet, but from an asteroid. 3200 Phaethon, a rock that may be an extinct comet that shed all its volatiles and now consists only of the rocky core. The Geminids can produce up to 120 meteors per hour during peak activity, bright, multicolored streaks visible from anywhere on Earth, weather permitting. They're a reliably spectacular show, the kind of event that gets news coverage and draws people outside even in December cold. Finally, the Perseids on December 21st and 22nd, radiating from the constellation Ursa Minor debris from Comet Tuttle. The Perseids are typically sparse, maybe 5 to 10 meteors per hour, and they suffer from unfortunate timing, peaking around the winter solstice when nights are longest in the northern hemisphere but weather is often poor. They're the quiet closing act of the year's meteor calendar. Less impressive than the Geminids, but still a regular feature of the December sky. 3 major showers across 5 weeks, overlapping with Atlas's passage through the inner solar system, overlapping with the supermoon, overlapping with increased solar activity from that coronal hole. If you were designing a period of maximum celestial business, maximum sky activity, maximum reasons for people and instruments to be looking upward, you couldn't schedule it much better than this. The universe has delivered a spectacular autumn and early winter, a season of cosmic displays that will keep astronomers and casual observers engaged for months. And here's where the pattern raises questions. When meteor showers cluster, when the sky is regularly streaked with expected phenomena, the observational environment becomes more complex. Every unknown object has to be distinguished from the known background. Every anomalous observation competes for attention with spectacular but explicable events. The meteors are beautiful, worth watching, scientifically interesting in their own right. But they're also noise from the perspective of tracking other objects there. A baseline of activity that other signals have to rise above to be noticed. Could interstellar fragments, dust clouds following Atlas's trajectory, particles shed during its passage through our solar system, could any of these coincide with regular meteor showers? Could material from another star system be entering Earth's atmosphere right now, burning up alongside Leonid or Geminid meteors, misclassified or simply unnoticed? Because we expect to see meteors during these periods, and we see what we expect. The chemistry would reveal the truth if we looked closely enough, but we're not capturing detailed spectra of every meteor. We're not analyzing every streak. The vast majority of meteors are observed visually, photographed perhaps, and that's it. Only a tiny fraction get the detailed scientific attention that would reveal unusual composition. So if interstellar material is mixed in with solar system material, if anomalous particles are hiding among expected particles, the odds of detection are low unless something is obviously different, spectacularly strange, impossible to misclassify. There's also a human element here. When celestial events are baked into the calendar, when they're expected and anticipated and normalized, they become part of the background reality. The Geminids happen every December. The Leonids happen every November. These are facts, regular occurrences as predictable as seasons. They're not mysteries. They're not anomalies. Their cosmic infrastructure, the regular rhythm of Earth's journey around the Sun, carrying us through debris streams left by various comets and asteroids. This normalization is useful. It allows us to predict and prepare for events. It lets US schedule observations and public outreach. It turns chaotic cosmic phenomena into comprehensible patterns. But it also creates blind spots. When something is normalized, we stop questioning it. We stop looking at it with fresh eyes. We classify and file and move on. And if something genuinely unusual is hiding within the normalized pattern, we might miss it entirely because we've trained ourselves not to look too closely at events we think we understand. The clustering of these showers around Atlas's passage could be pure coincidence. Orbital mechanics care nothing for our narratives. Earth's path through various debris streams is determined by gravitational laws that operate independently of what interstellar objects happen to be passing through simultaneously. There's no reason to think that timing is coordinated or meaningful, except timing creates context. When major news stories break during periods of distraction, they get less attention. When significant developments happen while the public is focused elsewhere, they can be overlooked or underplayed. The same principle might apply cosmically. When the sky is full of expected spectacles, when meteor showers and supermoons and other regular phenomena dominate attention, anomalies can pass with less scrutiny than they'd receive during quieter periods. This isn't necessarily deliberate. It doesn't require conspiracy or coordination. It's just the natural result of attention being finite, of there being only so many hours in the night, only so many telescopes to point at the sky, only so much processing capacity for data analysis. When there's a lot happening, not everything gets equal attention. Priorities get set, resources get allocated, and some things, potentially important things, might get relegated to lower priorities simply because they're competing with more immediate or more spectacular events. So as the Leonids streak and the Geminids blaze and the Ursids close out the year, remember that you're watching a curated show, not curated by any human hand, but curated by the limitations of attention. An observation: what you see is what's brightest, most obvious, most expected. What you don't see might be more important. Hidden in the darker spaces between the meteors, moving through the sky while your eyes track the streaks. Which brings us to the final. The question we've been circling throughout this investigation. Are all these cosmic events, these moons and meteors and holes and anomalies, are they just timing? Just coincidence? Just the universe being busy in multiple unrelated ways simultaneously? Or is there something larger at play? Some pattern we're not recognizing because we're too close to see it clearly. Let's step back and examine the calendar itself and ask whether we're living through a countdown to something we haven't identified yet. Calendar or countdown, look at what we've assembled. An interstellar object with anomalous properties passing through our solar system, a rogue black hole wandering our galaxy, a massive coronal hole disrupting solar observations. Cosmological papers suggesting the universe might crunch rather than expand forever. Satellites falling daily, creating observational noise. A supermoon capturing public attention. 3 major meteor showers clustered across 5 weeks. The cold moon rising with all its symbolic weight of endings and closure. Each of these, taken individually, is explicable, natural, expected, or at least not unexpected. The universe is large and busy, and strange things happen regularly. Finding multiple strange things happening simultaneously shouldn't surprise us. The sample space is huge. The number of potentially interesting cosmic events is vast. Some overlap is inevitable. Clusters occur in randomness. Coincidences happen. Seeing pattern here is just pareidolia, the human tendency to perceive meaningful connections in meaningless noise. This is the safest interpretation, the one that requires no special pleading, no exotic hypothesis. It's probably right. Second, frame, narrative camouflage. Not conspiracy, not coordination, but a structural condition where genuine anomalies benefit from occurring during periods of high noise and distraction. If Atlas is something unusual, something that would attract intense scrutiny during quieter periods, its passage during a season of spectacles provides natural cover. Not because anyone planned it that way, but because the busy, observational environment makes it harder to focus, harder to confer, easier to dismiss or defer for later analyses. Under this frame, the timing doesn't have to be deliberate to be consequential. The effect exists regardless of intent. Third frame, cosmic choreography. This is the most speculative, the hardest to defend, but worth articulating. What if these events are connected at a level we don't recognize? What if Atlas is part of something larger, a phenomenon or process that affects multiple aspects of the cosmic environment simultaneously? We've been assuming these are independent variables, separate events happening in parallel. But what if they're coupled somehow? What if rogue black holes and interstellar visitors and solar activity and even media stream distributions are linked through mechanisms we haven't discovered yet? Under this frame, we're not seeing coincidence. We're seeing a pattern whose logic remains hidden because we lack the theoretical framework to recognize it. Each frame has strengths and weaknesses. The coincidence frame is parsimonious but potentially dismissive of genuine anomalies. The camouflage frame acknowledges structural effects without requiring intent but might overinterpret noise. The choreography frame is intellectually exciting but demands evidence we don't have and probably won't get. Choosing between them requires weighing not just data but philosophical commitments about how the universe works. Whether it contains hidden patterns, whether coincidence is always just coincidence. What's clear is that the celestial calendar for late 2025 has delivered an unusually rich collection of events. Whether that richness is random or meaningful, whether the timing aids or hinders discovery, whether we're living through cosmic business as usual or something more significant. These questions can't be definitively answered with the information available. We're left in uncertainty, watching the sky, tracking the schedule, wondering if the calendar is counting time or counting down to something. And here's the final uncomfortable thought. Maybe the question itself is the point. Maybe what matters isn't whether Atlas is natural or artificial, whether the timing is coincidental or choreographed, whether we're witnessing something extraordinary or just misinterpreting the ordinary. Through the lens of our hopes and fears, maybe what matters is that we're asking these questions at all, that we're looking up, that we're grappling with uncertainty rather than retreating into false certainty. The narrative around Atlas, the story we're constructing about what it is and what it means, that narrative says as much about us as it does about the object itself. It reveals how we handle ambiguity, whether we rush to conclusions or sit with not knowing, whether we trust institutions or question them, whether we're willing to entertain uncomfortable possibilities or whether we need the universe to behave in expected ways for our psychological comfort. So look up, watch the cold moon rise, count the meteors as they streak, notice the supermoon's brightness and the darkness around it. Track Atlas as it passes through our solar system and disappears back into the interstellar void. But also look inward. Notice what you want to believe and why. Notice what makes you uncomfortable and what that discomfort protects you from feeling. Notice the stories you tell yourself about what's happening in the sky and recognize them as stories. Human constructions layered over phenomena that exist independent of our interpretations. The calendar continues. The countdown, if there is. A countdown proceeds according to schedules we don't control. Events will unfold. Data will eventually be released or remain withheld. Questions will be answered or will transform into new questions. And we'll be here watching, wondering, constructing narratives, because that's what humans do when faced with mystery. Who wrote this schedule? The clustering of cosmic events across these specific months. Did anyone write it? Or is that question itself a category error, an attempt to impose authorship on processes that simply are? The universe doesn't write, it doesn't plan, it unfolds according to laws we partially understand, producing patterns that sometimes look designed but might just be the inevitable result of complexity iterating across vast timescales. Or maybe, just maybe, some patterns are designed, some timing is deliberate. Some objects passing through our sky carry intent, rather than just momentum. We don't know. We can't know, not yet. Not with what we can currently observe and measure, but we can remain open to the possibility while avoiding the trap of certainty in either direction. If you believe the narrative about Atlas being just a comet, you might be right. You might also be missing the most important discovery in human history because you preferred comfort over discomfort, certainty over uncertainty, the known over the genuinely alien. If you believe the narrative about Atlas being something more, you might be right. You might also be pattern matching on noise, seeing design in randomness, constructing elaborate theories to explain data that has simpler explanations. The only intellectually honest position is doubt combined with attention. Doubt that we know enough to conclude definitively, attention to what the universe is showing us, even when it's uncomfortable or ambiguous. The sky doesn't care what we believe about it, it just is. And we, temporary observers with limited instruments and biased interpretations, do our best to read its messages written in light and gravity and the motion of objects across unimaginable distances. Look up, but also ask who wrote the schedule, if anyone did. Ask what you're leaving unseen while you watch what's most visible. Ask whether the narrative you've accepted is one you chose or one you were given. The cosmos is vast and strange and indifferent to human storytelling. But we're storytelling animals, and the stories we tell about what's above us shape how we understand what we are. So tell those stories carefully, question them rigorously, and remember that the truest answer to cosmic mysteries might always be, at least for now, simply this: we don't know, but we're watching, and that watching itself is the beginning of wisdom. The cosmic theater and its unseen audience. Let's zoom out for a moment and consider the stage itself. We've been focusing on the Actus Atlas, the rogue black hole, the sun's wound, the falling satellites, the meteor showers. But what about the theater? What about the cosmic environment in which all these events are playing out? What if we're missing something fundamental about the nature of space itself? something that would make sense of the apparent chaos we're witnessing. Quantum physics tells us that at the smallest scales, reality is probabilistic, fuzzy, deeply weird. Relativity tells us that at the largest scales, space-time is curved, dynamic, capable of bending and stretching in ways that defy our everyday intuition. But between these scales, in the middle ground where planets orbit and stars shine and galaxies rotate, we tend to think of space as a relatively stable backdrop, inert, a passive stage on which cosmic events play out. What if that's wrong? What if space itself is more active, more responsive, more participant than we've assumed? What if the clustering of anomalies we're witnessing isn't just coincidence or camouflage or choreography, but evidence of a universe that's fundamentally more interconnected than our current models allow? There are hints in the data that point in this direction. Quantum entanglement shows that particles can remain connected across vast distances, influencing each other instantaneously in ways that seem to violate the speed of light limit. Dark matter and dark energy suggest that most of the universe is composed of substances we can't directly detect, but that exert profound influence on cosmic structures. Recent work in quantum gravity proposes that space-time itself might emerge from more fundamental quantum processes, making it less like a fixed stage and more like a dynamic participant in cosmic evolution. If space itself has properties we're not recognizing, if the vacuum between stars is not truly empty but filled with fields and connections we can't yet measure, then the apparent separation between cosmic events might be illusory. The rogue black hole, Atlas, the coronal hole, the meteor showers, these might not be independent phenomena at all, but different manifestations of the same underlying process, different ripples on the same cosmic pond. This is highly speculative, bordering on metaphysics, but it's worth considering because it offers a framework that could explain the clustering of anomalies without invoking coincidence or conspiracy. In a universe where everything is fundamentally interconnected, where information can flow through channels we don't yet understand, where the fabric of space-time itself can respond to events in ways we haven't yet measured, the patterns we're seeing might make perfect sense. There's historical precedent for this kind of paradigm shift. Before Einstein, space and time were thought to be absolute, fixed, independent of the matter and energy within them. Relativity revealed that space and time are dynamic, interwoven, responsive to gravity and motion. Before quantum mechanics, the universe was thought to be deterministic, predictable at least in principle. Quantum theory revealed that at its most fundamental level, the universe is probabilistic, uncertain, deeply strange. Each paradigm shift revealed that the universe was weirder and more wonderful than we had imagined. Each required us to abandon comfortable assumptions and embrace counterintuitive realities. Perhaps we're due for another such shift, a recognition that the cosmos is more interconnected, more responsive, more alive than our current science. Alas, if this is true, it has profound implications for how we should interpret events like Atlas's passage. Rather than asking whether it's natural or artificial, we might need to ask whether that distinction is even meaningful in a universe where the boundary between natural and artificial, between random and designed, between independent and coordinated, might be fundamentally different than we assume. This doesn't mean we should abandon critical thinking or accept every wild speculation, but it does suggest that we should hold our categories lightly, remain open to the possibility that the universe operates according to principles we haven't yet discovered, and recognize that the patterns we're seeing might be clues to a deeper reality rather than just random coincidences. The philosopher Alfred North Whitehead proposed a view of nature he called process philosophy, which sees the universe not as a collection of static objects, but as a web of interconnected processes, each influencing and being influenced by the others. In this view, what matters is not what things are, but what they do, how they relate, how they participate in the ongoing evolution of cosmic reality. Perhaps we're witnessing evidence of this process view in action. Perhaps the clustering of cosmic events isn't a problem to be solved, but a revelation to be embraced, a glimpse of the universe's fundamental interconnectedness. A reminder that the boundaries we draw between phenomena are more about our limited perception than about the nature of reality itself. This perspective doesn't answer the specific questions about Atlas's composition or origin or purpose, but it does suggest that those questions might be missing the point. Maybe the important thing isn't what Atlas is, but what its appearance reveals about the nature of the cosmos, about the hidden connections that bind seemingly separate events into a coherent whole as we continue to watch the sky, as we track the unfolding cosmic drama of late 2025. Perhaps we should expand our perspective beyond the individual actors and consider the stage itself. Maybe the most important discovery won't be about what Atlas is made of or where it came from, but about the fundamental nature of the space through which it travels, the invisible threads that connect it to everything else, the cosmic dance in which we are all participants, whether we recognize it or not. The cosmic mirror what Atlas reflects about us. Let's shift gears for a moment and consider a different angle. Throughout this investigation, we've been asking what Atlas is, where it came from, what it's doing here, but maybe we should be asking a different question. What does Atlas reveal about us? How does our response to this cosmic anomaly reflect our values, our fears, our aspirations, our limitations as a species? The way we interpret ambiguous evidence says a lot about our psychological predispositions. Those who lean toward natural explanations tend to value caution, skepticism, adherence to established paradigms. They're often uncomfortable with uncertainty, preferring to maintain existing frameworks even when faced with anomalies. Those who lean toward artificial explanations tend to value openness, imagination, willingness to challenge orthodoxy. They're often more comfortable with ambiguity, more willing to entertain possibilities that stretch the boundaries of current understanding. Neither tendency is inherently better or worse. Both have their place in the scientific enterprise. Both reflect different aspects of human cognition. But when these tendencies become rigid identities, when they transform from methodological approaches into ideological positions, they become obstacles to understanding rather than pathways to truth. The institutional response to Atlas reveals something about the structure of scientific knowledge production. Space agencies operate within constraints of funding, public perception, political oversight. They balance the imperative to share knowledge with the need to maintain credibility. They navigate between transparency and caution, between the desire to inform and the risk of misinforming. These tensions are failures of the system. They're features of any complex human organization dealing with uncertain, high-stakes information. The public response to Atlas reveals something about our relationship with authority and expertise in an era of declining trust in institutions. When information is abundant, but wisdom is scarce, when anyone with an internet connection can position themselves as an expert, the gap between official narratives and alternative explanations becomes a battleground for competing worldviews. How we navigate this gap, whether we default to trust or skepticism, whether we seek consensus or controversies, is as much about our social and political orientations as it does about our assessment of the evidence. The media response to Atlas reveals something about our information ecosystem. Traditional news outlets, with their emphasis on verification and balanced reporting, often lag behind the story, publishing cautious takes after the most interesting moments have passed. Social media platforms, with their emphasis on immediacy and engagement, amplify the most dramatic interpretations, creating feedback loops that reinforce existing beliefs. Alternative media outlets, with their emphasis on questioning official narratives, sometimes offer valuable perspectives but often veer into unsubstantiated speculation. Each platform shapes the story in different ways, creating multiple versions of reality that coexist in the same information space. The scientific response to Atlas reveals something about the culture of research. The peer review process, designed to ensure quality and rigor, can also serve to maintain paradigm boundaries, making it harder for genuinely novel ideas to gain traction. The specialization of modern science, while necessary for advancing knowledge, can create silos that inhibit interdisciplinary thinking. The competition for funding and recognition, while motivating, can incentivize conservative research that's more likely to produce publishable results than revolutionary insights. None of these observations are criticisms as much as descriptions of the complex ecosystem through which we come to know what we know about the universe. Understanding this ecosystem is as important as understanding the cosmic phenomena themselves. Because the way we construct knowledge shapes what we think we know, Atlas serves as a mirror, reflecting back to us our collective strengths and weaknesses, our curiosity and our fear, our capacity for wonder and our tendency to pattern match, our ability to build sophisticated instruments that can detect objects from other star systems, and our inability to agree on what those detections mean, our scientific achievements and our philosophical limitations. Perhaps the most valuable thing about Atlas isn't what it teaches us about interstellar objects or cosmic chemistry or solar dynamics, but what it teaches us about ourselves, how we respond to the unknown, how we handle uncertainty, how we balance skepticism and openness, how we construct shared reality from ambiguous evidence. These are fundamentally human questions that Atlas brings into sharp relief. In this sense, the investigation of Atlas becomes an investigation of human consciousness itself. Our attempts to understand the cosmic other are also attempts to understand ourselves. The questions we ask about Atlas reveal what we value, what we fear, what we hope for. The answers we accept or reject reflect our deepest assumptions about the nature of reality and our place within it. This doesn't mean we should abandon the scientific investigation of Atlas or stop trying to determine its true nature. But it does suggest that we should approach this investigation with a degree of self-awareness, recognizing that our observations are filtered through the lens of human consciousness, that our interpretations are shaped by cultural and psychological factors we're not always conscious of, that the story we ultimately tell about Atlas will say as much about us as it does about the object itself. As we continue to follow Atlas's journey through our solar system, as we analyze the data and debate the interpretations, perhaps we should also turn some of our analytical attention inward. What does our response to this cosmic visitor reveal about our collective psyche? What does it show us about our relationship with the unknown, with each other, with the universe itself? In the final analysis, Atlas might be the most important interstellar object we've ever encountered, not because of what it is, but because of what it shows us about ourselves, and that, perhaps, is the most profound discovery of all. The quantum lens rethinking observation itself. Let's push our speculation even further and consider a possibility that challenges the very foundation of how we think about cosmic observation. What if the act of observing Atlas is changing what we're observing? What if our collective attention, our instruments, our questions are not just passive recipients of information, but active participants in creating the reality we're trying to understand? In quantum mechanics, the observer effect demonstrates that at the quantum scale, the act of measurement inevitably changes the system being measured. Particles exist in superpositions of states until observed, at which point they collapse into definite states. The observer and observed are not separate but deeply entangled in the creation of reality. Most scientists would argue that this quantum weirdness doesn't apply to macroscopic objects, like comets or asteroids. The decoherence effect ensures that quantum behavior is averaged out at larger scales, creating the classical world of definite objects with predictable properties. But what if this separation between quantum and classical realms isn't as sharp as we think? What if there are ways in which the observer effect extends beyond the quantum scale, especially in situations that involve unusual objects or unusual observational conditions? Atlas is not a typical comet. It's an interstellar visitor with properties that challenge our categories. It's being observed by an unprecedented array of instruments, by a global network of professional and amateur astronomers, by a public that's more connected and engaged than ever before. The collective attention focused on Atlas represents a massive concentration of observational energy, a quantum measurement on a cosmic scale. What if this concentrated attention is having an effect? What if the boundary between observer and observed is more porous than we assume, especially when the observed is already anomalous and the observation is unusually intense? This sounds like New Age mysticism rather than hard science, but there are precedents in physics that suggest we should be cautious about dismissing such possibilities out of hand. The delayed choice experiment in quantum mechanics shows that decisions made by observers can affect the behavior of particles that have already been detected, suggesting a retrocausality that violates our usual understanding of time and causality. Entanglement demonstrates that particles can remain connected across vast distances, influencing each other instantaneously in ways that seem to transcend the speed of light limit. Recent work in quantum foundations suggests that information might be more fundamental than matter or energy, raising the possibility that consciousness itself plays a role in the construction of reality. These are fringe ideas, not mainstream physics, but they are taken seriously by reputable scientists and have experimental support, however limited. They suggest that our understanding of the relationship between consciousness and reality is still evolving, that the boundary between observer and observed might be more permeable than our classical intuitions allow. If we apply these ideas to Atlas, several speculative possibilities emerge. Perhaps the anomalies we're observing, the unusual light curve, the extreme polarization, the non-gravitational acceleration are not intrinsic properties of the object, but manifestations of the observer effect, reflections of our collective attempt to understand something that defies our categories. Perhaps the ambiguity surrounding Atlas is not just a limitation of our instruments, but a fundamental feature of reality when confronted with unusual objects and unusual observational conditions. Perhaps, in a sense, we're co-creating the reality of Atlas through our observations, our questions, our expectations. The object might be responding to our attention, not in a conscious or intentional way, but through the fundamental interconnectedness of observer and observed at the quantum level. This doesn't mean Atlas is imaginary or that its physical properties are entirely subjective, but it does suggest that the sharp division between objective reality and subjective observation might be more fuzzy than we typically assume. This perspective has profound implications for how we should approach the investigation of Atlas. If our observations are influencing what we're observing, then the methodological ideal of detached, objective observation becomes problematic. We need to find ways to observe that are less intrusive, less disruptive to the system being studied. We need to develop a form of cosmic etiquette that acknowledges our participation in the reality we're trying to understand. We also need to be more reflective about our own role in the investigative process. What questions are we asking? What assumptions are we bringing to the table? What expectations are shaping our observations? By becoming more aware of our own influence on the outcome, we might be able to minimize unintended effects and obtain clearer data. This doesn't mean we should abandon rigorous scientific methodology or accept every wild speculation about the nature of reality. But it does suggest that we should approach the investigation of Atlas with a degree of humility, recognizing that our understanding of the relationship between consciousness and reality is still incomplete, that the boundary between observer and observed might be more permeable than we assume. The quantum perspective also offers a potential resolution to some of the paradoxes surrounding Atlas. If the object exists in a superposition of states natural and artificial, random and designed, independent and coordinated until observed, then the conflicting data and interpretations might not be failures of measurement, but reflections of a deeper quantum reality. The act of observation forces the object into a definite state, but different observations made with different assumptions and expectations might collapse the superposition in different ways, creating apparently contradictory results. This is highly speculative, pushing the boundaries of current physics into realms where experiment and theory are still catching up with imagination. But the history of science suggests that today's speculation often becomes tomorrow's established fact. The quantum revolution of the early 20th century transformed our understanding of reality in ways that seemed absurd to classical physicists. Perhaps we're due for another such revolution, one that will further blur the boundary between mind and matter, observer and observed. As we continue to study Atlas, perhaps we should also study ourselves as observers. Perhaps we should develop new methodologies that account for the observer effect. New ways of knowing that acknowledge our participation in the reality we're trying to understand. Perhaps the most important discovery will not be about what Atlas is, but about how we know what we know, about the fundamental relationship between consciousness and the cosmos. In this sense, Atlas might be more than just an interstellar object. It might be a catalyst for a new understanding of reality itself. A quantum key that unlocks doors we didn't even know existed. And that, perhaps, is the most profound possibility of all. The cosmic crossroads, choosing our future. As Atlas continues its journey through our solar system, approaching its closest encounter with the Sun and then beginning its long departure back into interstellar space, we find ourselves at a crossroads, not just in how we interpret this particular anomaly, but in how we approach the unknown more broadly. The way we respond to Atlas sets precedents that will shape our response to future anomalies, future discoveries, future encounters with the cosmic other. This crossroads presents us with three potential paths forward, each with different implications for how we'll navigate the mysteries that lie ahead. The first path is the path of conventional science. On this path, we treat Atlas as a natural but unusual object. We emphasize the need for more data. We wait for definitive evidence before drawing conclusions. We maintain the boundary between established science and speculative inquiry. This path values caution, rigor, adherence to established methodologies. It minimizes the risk of false positives, of jumping to conclusions that later prove unfounded. It preserves the credibility of scientific institutions and maintains public trust in the scientific process. The advantage of this path is its reliability. It has served us well for centuries, producing a steadily expanding body of knowledge about the universe. It provides a solid foundation for further investigation and creates a framework for distinguishing between speculation and established fact. The disadvantage of this path is its potential conservatism. By emphasizing what we know over what we don't, it might miss or dismiss genuinely anomalous phenomena that don't fit existing paradigms. By waiting for definitive evidence, it might delay recognition of revolutionary discoveries until the window of opportunity has passed. By maintaining strict boundaries between disciplines, it might overlook insights that emerge from interdisciplinary approaches. The second path is the path of radical openness. On this path, we treat Atlas as potentially evidence of something beyond our current understanding. We embrace uncertainty as a productive state. We encourage speculative inquiry even in the absence of definitive evidence. We blur the boundaries between established science and frontier exploration. This path values imagination, creativity, willingness to challenge orthodoxy. It maximizes the potential for breakthrough discoveries, for paradigm shifts that transform our understanding of reality. The advantage of this path is its potential for revolutionary insight. By entertaining possibilities that stretch the boundaries of current knowledge, it opens doors to new ways of thinking, new frameworks for understanding cosmic phenomena. By encouraging speculation, it creates a fertile environment for innovative ideas that might eventually lead to breakthrough discoveries. The disadvantage of this path is its potential for unrestrained speculation. By blurring the boundaries between evidence and imagination, it risks creating a landscape where unfounded claims receive the same attention as rigorously tested theories. By embracing uncertainty too enthusiastically, it might undermine public trusts in scientific expertise and create confusion about what we know and what we don't know. The third path is the path of integrated inquiry. On this path, we recognize the value of both conventional science and radical openness. We create spaces where different approaches can coexist and inform each other. We develop methodologies that balance rigor with imagination. We cultivate a culture of inquiry that values both established knowledge and frontier exploration. This path acknowledges that different kinds of questions require different kinds of answers, that the universe is complex enough to accommodate multiple ways of knowing. The advantage of this path is its balance. By integrating the strengths of different approaches, it creates a more comprehensive framework for investigation, one that can both build on existing knowledge and remain open to revolutionary insights. By fostering dialogue between different perspectives, it creates opportunities for synthesis and emergence, for new understandings that transcend the limitations of any single approach. The disadvantage of this path is its difficulty. It requires navigating tensions between different methodologies, different epistemological frameworks, different institutional cultures. It demands a level of intellectual flexibility and institutional adaptability that might be challenging to achieve in practice. Which path we choose will have profound implications, not just for how we investigate Atlas, but for how we approach the broader project of cosmic discovery. The universe is vast and strange, and it will continue to present us with anomalies that challenge our understanding. Our response to these anomalies will shape not just what we know, but who we become. As a species, perhaps the most important thing to recognize is that these paths are not mutually exclusive. Different questions might require different approaches. Different stages of investigation might call for different methodologies. The ideal approach might be one that can move fluidly between different modes of inquiry, drawing on the strengths of each as appropriate. As we stand at this cosmic crossroads, perhaps the most important question is not which path to choose, but how we might integrate the wisdom of all three. How can we maintain the rigor of conventional science while remaining open to revolutionary possibilities? How can we encourage speculative inquiry without losing our grounding in evidence? How can we create a culture of cosmic discovery that is both disciplined and imaginative? The answer to these questions will determine not just how we understand Atlas, but how we navigate the ongoing mystery of existence itself. The universe continues to unfold in ways that surprise and challenge us, offering glimpses of realities that transcend our current understanding. How we respond to these offerings, whether with caution or courage, with skepticism or openness, with established methods or innovative approach, will shape not just what we know, but who we become. As Atlas continues its journey, perhaps we should see it not just as an object to be studied, but as a mirror reflecting our own choices, a catalyst prompting us to reflect on how we want to engage with the cosmic unknown. The path we choose in response to this interstellar visitor will set precedents that echo far beyond this particular investigation, influencing how we approach all the mysteries that lie ahead. In this sense, Atlas is more than just a cosmic anomaly, a cosmic crossroads, an invitation to choose not just what we believe about this particular object, but how we want to relate to the universe itself. And that choice, perhaps, is the most important discovery of all. The cosmic invitation, looking forward, looking back, as we reach the conclusion of this investigation, with Atlas approaching its closest encounter with the Sun and preparing to begin its long journey back into the interstellar void. It's worth taking a moment to reflect on what we've learned, not just about the object itself, but about ourselves, our methods, our relationship with the cosmos. We've examined the anomalies that make Atlas so puzzling. Its unusual light curve suggesting structured geometry rather than chaotic tumbling. Its extreme polarization that defies standard cometry models. Its carbon dioxide-dominated outgassing with barely any water. The nickel signatures that shouldn't appear in natural comets. The non-gravitational acceleration that doesn't fit conventional outgassing models. Each of these anomalies, taken individually, might be dismissed as a minor puzzle. Together, they form a pattern that challenges our understanding of what comets are and how they behave. We've explored the institutional context surrounding Atlas, the careful vetting of public statements, the gaps between observation and announcement, the missing data from instruments that should have captured better images, the incentive structures that push agencies toward caution and conventional explanations. These institutional factors don't prove that anything is being hidden, but they do create conditions where speculation flourishes and trust erodes. We've considered the broader cosmic context in which Atlas appears, the rogue black hole wandering our galaxy, the massive coronal hole disrupting solar observations, the cosmological papers suggesting the universe might crunch rather than expand forever, the satellites falling daily, creating observational noise, the clustering of celestial spectacles, the supermoon, the meteor showers, the cold moon that might be masking or distracting from the anomaly at the center of our story. We've ventured into speculative territory, exploring possibilities that stretch the boundaries of current understanding. The idea that Atlas might be artificial rather than natural. The suggestion that the clustering of cosmic events might reflect a deeper interconnectedness we don't yet recognize. The proposal that our observations might be influencing what we're observing through a cosmic scale observer effect. The notion that the boundary between natural and artificial, between random and designed, might be fundamentally different than we assume. Throughout this investigation, we've maintained a balance between skepticism and openness, between rigorous analysis and imaginative speculation, between what we know and what we don't know. We've recognized that uncertainty is not a failure to be resolved, but a condition to be embraced, a space where genuine inquiry can flourish. As we conclude, perhaps the most important insight is that Atlas, regardless of its ultimate nature, serves as an invitation to expand our understanding, to question our assumptions, to embrace mystery rather than rushing to closure, to recognize that the universe is stranger and more wonderful than our current categories can contain. This invitation comes at a crucial moment in human history. We face global challenges that demand new ways of thinking, new approaches to problem solving, new relationships with each other and with the planet we call home. The cosmic perspective offered by Atlas reminds us that we're part of something larger than ourselves, participants in a cosmic drama that stretches across unimaginable scales of space and time. In this sense, the investigation of Atlas is not just about understanding an interstellar object. It's about understanding ourselves and our place in the cosmos. It's about developing the intellectual and spiritual tools we need to navigate a future that will undoubtedly present us with mysteries that challenge our current understanding as profoundly as Atlas challenges us today. As Atlas disappears back into the darkness between stars, it leaves us with questions rather than answers, with wonder rather than certainty, with a sense of possibility rather than closure. And perhaps that's exactly what we need. Not definitive solutions to cosmic puzzles, but an ongoing invitation to explore, to question, to marvel at the mystery of existence. The cosmic story continues to unfold, with or without our understanding. New anomalies will appear, new questions will emerge, new opportunities for cosmic discovery will present themselves. How we respond to these invitations will shape not just what we know, but who we become. So look up, watch the sky, follow the unfolding cosmic drama with attention and wonder. But also look inward. Notice how you respond to mystery, how you balance skepticism and openness, how you navigate the space between what you know and what you don't know. The cosmic mirror reflects not just the objects we observe, but the observers we are. Atlas is leaving our solar system, but the invitation it represents remains an invitation to expand our understanding, to embrace uncertainty, to recognize that the universe is not a collection of objects to be categorized, but a mystery to be engaged, a dance to be joined, a conversation to be continued across the vast expanses of space and time. In the end, perhaps the most important discovery is not what Atlas is, but what the investigation of Atlas reveals about us or our capacity for wonder, our hunger for understanding, our ability to hold multiple possibilities simultaneously, our willingness to engage with mystery rather than retreat into false certainty. These qualities, curiosity, openness, intellectual humility, courage in the face of the unknown, are perhaps the most valuable things we bring to our cosmic encounter. They are the qualities that will serve us well as we continue to explore the universe and our place within it.